The purpose of today's class, I guess, webinar, whatever you want to call it, is to cover a little bit on what we learned on mostly the ART.E project, but obviously we've done a bunch of other RL projects here, so I'll definitely share more general insights where possible. And then also help, hopefully people on this call get a sense of, all right, is RL good, useful for me? Is this something that I should be considering for a project I'm working on right now? And then of course, if you are considering it, sort of what the prerequisites are to get that. So I'm Kyle, I'm the CEO of OpenPipe. We've been doing this for a couple of years. OpenPipe is a hosted platform for model customization with both SFT, RL, other things like DPO, which are sort of somewhere in the middle. We also are working really heavily on a library called ART, which is an OpenPipe project, which is a trainer for doing multi-turn rollouts with reinforcement learning. It integrates really nicely. If you're using like the OpenAI SDK, for example, you can just use that directly with this and then directly optimize those traces. So we've tried to make it really easy to get started if you're coming from, hey, I have something deployed in production and I want to use RL to make it better. So definitely check that out. I'll have links at the end of the presentation to that library. Okay. So I divided this into 4 parts. I think that they build on top of each other, and it's important that we cover all of them so we're on the same page. Part 1, what is an agent? Yes, I realize we all have heard of agents, but also it seems like every person I talk to has a different definition. So for the purposes of this presentation, I'll talk about what I mean by an agent. Part 2 is optimizing your agent. So this is really going to be the meat of the presentation with, okay, you have this agent, you're trying to get it to do something. How can I use RL to make it much stronger, much better at the task I'm trying to accomplish? And then part 3, we'll talk a little bit about sort of generalization, taking the lessons learned in part 2 and applying them to other domains where hopefully other, that's useful for you figuring out what you want to or can potentially use RL for. And then we'll have open questions and answers at the end. So my rough estimate is that parts 1 through 3 will take maybe the next 20-ish, maybe 25 minutes. And then we should save a nice chunk of time at the end for questions. There is a Q&A feature built into Google Meets, which you can go ahead and use to submit those questions. And that way I can mark them off as I answer them, and it'll be a little bit better managed. So feel free to drop those in at any time as the meeting's going on. Cool. Okay. So we're going to go ahead and get into it. So to give a little bit of background on the example project we're using as we go through these 4 phases. It's a project called ART.E. It is an email search assistant that we built as a case study of basically how all these technologies work together. Importantly, it works really, really well, which is one of the reasons it's a good case study. We found that for the purposes, so basically the task it's trying to do is, I have a natural language question about something that is in my email inbox. This agent's purpose is to take that natural language question, go and search the email inbox, and then try and find what are the relevant emails and extract the answer and give it back to you. So you can see based on the stats, the benchmarks we have here, that it was able to outperform every other agent, every other LLM we used as part of this agentic flow. And so we were able to get the correct answer 96% of the time on our test set versus just 90% of the time with O3, which was the next best performing model. We'll get into some of this as we're talking about why you might want to use RL later on, but beyond just getting incrementally better accuracy, we find that there's like key benefits on the latency side and the cost side as well, both of which, depending on your specific flow, could be really relevant. I think latency is probably relevant for almost everyone. We found, for example, with O3, that the average like full end-to-end time from I asked my question to I get my answer back was 5.6 seconds on average, whereas with ART.E, it was able to get the answer back in 1.1 seconds through a combination of just being a faster model, because it's a much smaller one, and also, as we'll see later in the presentation, using fewer terms. So that's the example project, which we'll be going over and explaining more how that works as we get into it. Okay, so let's define terms, what I'm talking about when I say an agent. I have like a pretty simple definition in my mind, which is an agent is an LLM-powered system that has an objective. So there's something it's actually trying to accomplish, and then it's given tools to do that, right? So those can be exposed via like an MCP server. They can be exposed just by, sort of like writing manual code in your code base to say, hey, if the LLM's output is this, that means call this tool and call that function. There's different ways, but the important thing is that it does have tools and a way to act. Other optional elements that often end up in the package with this is reasoning. So it's often very helpful for the agent to not just be forced to immediately call a tool given its set of observations, but actually to first think through it and figure out, hey, what is the right next step? Maybe even like planning ahead of time. And then also memory is another thing that comes up very frequently in agentic applications, where it's sort of like a scratch pad, or maybe, it could be some kind of like hierarchical summarization of what it's done so far, but basically a way to track what have I done so far, what my plan is, what I'm trying to get done. Those are both elements that often show up in agentic applications. Importantly, I think in my opinion, an important part of an agent is that it does have sort of a self-directed control flow. And what do I mean by that? I mean, it's not sort of a harness where, you have hard-coded, okay, first you do this planning step, and then you, get this piece of information, then you get this piece of information. There's sort of like a predefined flow. The idea is that the agent, there's some kind of loop involved where the agent can decide what its next step is, and when it's done, whether to terminate. So there's some amount of self-direction, and that freedom is, I think, both a way to get more power out of the newest, most powerful models, which just have the ability to use that flexibility for more effectiveness. And also it gives you much more power if you do end up going with reinforcement learning, which of course is what this presentation is about. It's great to basically RL, if you give it that additional degree of freedom, it can optimize on that and you can end up with better performance. Okay, so that's what we mean by an agent. Yeah, talking about ART.E, I already introduced that project. But it fits this definition of an agent. It's a simple agent, but definitely agentic. So the objective is, as I mentioned before, we've got a natural language query. We're trying to answer it. The tools we're giving it, so ART.E, we gave it 3 specific tools to work with. And these are basic, but sometimes people come to me and they're like, hey, I have like 600 tools or something. It's like, I actually find it's often easier to have fewer tools and make them more powerful. As just a general heuristic, obviously, sometimes you need a lot of tools. In this case, we just had 3 tools. In this case, we have a tool that is search. So that's basically, it lets our LLM, put in keywords effectively, and a few other filters. So, like the from address, to address, like a date filters, it has the option to put those on. So it has the option to search the inbox. It has the option, and so when it runs a search, it gets back results. The results have the relevance, and they have the snippets from each email, and they have an email ID. And then it has the ability to read emails. So using those email IDs from search, it can read the contents of an email and see if it has the answer. And then finally, it has a special tool, which is like, hey, answer the email, answer the user's query based on the information you know so far. So really simple, but yeah, it does that in a loop. It decides which of those tools it wants to call. It decides when it's done. It calls the answer tool. If it decides, hey, I've tried everything I can't figure out the answer here, then it can go ahead and finish the loop. So it does have that self-directedness. So this is an example of basically, So this is an example of the agent going ahead and calling it. So this is just to get a sense with ART.E what it's actually doing, right? And I apologize. I hope that this text is legible. I should have made a larger one ahead of time, but I didn't. So basically, you can basically see here what the agent is actually doing. So we've got this just a system message. You're an email search agent. This is the user's email address, and you get today's date. And then we have the user query as the first message always. So the user says, hey, when is Sherry's move to Portland targeted for in this case? And then you can see what the agent is doing over on the right-hand column here. You can see, okay, first it calls the search emails tool. It's like, okay, Sherry Portland, that's reasonable. And it says, okay, I want something before the date I'm searching. All right, yeah, it makes sense. And we're going to get back from our system. We have a search implementation. It's going to give back the messages along with their snippets. And then so it looks like it's reading a specific email that it got from there. It's like, okay, so this one seems like it probably has the answer. It's going to read the email, and here's the email contents. And it says, aha, okay, so I think I have the answer now. And it responds with Sherry's move to Portland is targeted for the end of February. Okay, so that's basically the flow of how this search agent is implemented under the hood. All right, something that this is maybe a little bit tangential, but I do think that it's kind of potentially like useful as a framing, because it's something I've seen come up over and over again in different customer projects we're working on, which is a difference between what I've seen people calling agentic RAG versus just traditional RAG. So ART.E is a great example of agentic RAG, which is different than sort of what people have considered RAG in the past. Most of you are probably familiar. It stands for Retrieval Augmented Generation. The basic idea is if you want your LLM to be able to give good results, you need to give it the context that it's can use to get those results. So how traditional RAG worked was you would have semantic similarity. So you have your query, the question you're trying to answer. you would basically put that through an embedding model. The embedding model, you would also have like a big corpus. So in this case, if we were doing this with our email case with each of the emails we have, we would have put that through an embedding model as well. And then you would have basically taken that query you have and then find the emails that are most similar to it using this, basically according to this embedding similarity score that you're getting. You would grab those top 5 emails, 10 emails, whatever, that are most similar. You put them in context along with the question, and then you would tell your LLM, hey, based on this question I have, and then these emails that we got from our context, what is the answer? And you hope that the answer is in one of those emails, or that at least the LLM is smart enough to realize if it's not and not hallucinate, but just say, sorry, the answer is not here. So that's what we mean traditionally by RAG. Agentic RAG is sort of emergent approach that I've seen a bunch of people take. This is one of the big ways, like the new agentic flow in Cursor, for those of you who are engineers, works, right? Where instead of just implicitly, when you ask it to do something in the code base, it's sort of like pulling in, whatever the most similar snippets are from your code base. What Cursor does now with its agentic flow is it tells the LLM, hey, this is the problem I'm trying to solve. This is the method it's supposed to use. And then the LLM will actually go and be like, oh, okay, I'm going to grep the code base for, this string, something relevant to what you're trying to do, and see if there's other uses, pull those in. And so that's what we call agentic RAG, where instead of the system, the sort of outside system based on this semantic similarity, just telling it, hey, this is what I think is most similar, you're actually giving control, in a sense, back to your agent and saying like, hey, you are good at reasoning, you have a lot of background here. What do you think are the strings that we should search for in our code base, using typically lexical search or keyword search, and then pull in the context that way. It also, I think there's a few reasons why this is becoming more popular recently. One is that it does give the agent more control. So instead of just sort of like a one-time, okay, here's the results, good luck. If it's not there, then we're done. The agent can explicitly be like, oh, okay, that didn't give me the results I want. I want to go like search again. Another advantage is it's actually in some ways simpler, because with the sort of traditional RAG approach, you actually need a new piece of infrastructure. You need this vector database with embeddings that can pull the stuff in. With agentic RAG, typically you already have, because this is sort of the way humans work, is you'll grab your code base and things. So often there's like already tools available, because they're the same tools humans were using, that you can just put a nice wrapper around and give access to your agent. And then a third advantage is it's kind of a more unified paradigm in a lot of ways, because it's basically just one more tool, right? In the case of our agent here, it's this search email tool. And in, basically like, but if you want to have other tools, if like, let's say you're doing a customer support bot, right? You could have like a search, internal wiki tool, and then you could have a separate tool where it's like, oh, we need to escalate this case or something like that. It's like, I don't know what the right answer is. So you would just have a separate tool, which is escalate case. And it's a more unified paradigm, right? Because all your agent needs to understand how to do is use this list of tools, and you can add more tools over time. And so your search tool fits in very nicely with all your other tools. It's just one more tool in the toolbox. And you can use, for example, RL to optimize that directly by teaching it to use these tools effectively. Whereas if you want to optimize your RAG, you can do that. You can train an embedding model to work better to match these questions and these answers, but it's sort of a separate process from training your model to do all the other actions it might do. So you end up with a more unified and simple system with this agentic RAG approach. So that's the way that we decided to build it for our ART.E model. Feel free to drop questions if they're not sort of like general end of thing questions, but questions as I'm going, do feel free to drop them in the chat. It looks like a few people have already, and I'm going to go ahead and answer. Okay, so yeah, Jared's like, yes, dynamic embeddings is annoying. Yes, I've built fine-tuned RAG systems, and yeah, keeping it up to date is indeed annoying. Okay, so Jack asks, any limitations of agentic RAG, possibly such as evaluation? Yeah, I mean, let's see. Honestly, I think it works pretty well. I suspect that it's just going to be the dominant way that RAG is done going forward, because the main downsides, I would say, are maybe a little bit of performance and the floor on latency is higher because you have to wait for, okay, take the user input, wait for your agent to like formulate a query of what it wants to query the database, and then like run that query and give the agent back that context. So there is an extra round trip, as opposed to sort of traditional RAG where you're just doing that before you give anything to the LLM, you're already grabbing the context for it. So that could be a potential issue. depending on the use case, these models are getting fast enough at generating that like I think it's less of a concern than it might have been in the past. But yeah, that's one. On the evaluation side, I think anything you can do to evaluate sort of like semantic RAG systems, semantic search-based ones, will work here as well. I mean, you can just measure, oh, did my model put in the right keywords to get the right documents that are relevant, yes or no? And again, you can train it using RL to be much more effective at that, which is one of the things that we did here that we'll talk about in a bit on the ART.E side. Cool. Yeah, good question. Okay, so we've laid the groundwork. What do we think an agent is? Okay, now I'm going to talk about actually optimizing it, which is more of the meat here. So the first thing, which I always tell people we're working with, despite the fact that we're very focused on training here, is you really want to get as far as you possibly can before you actually do any training at all. And the reason why is because, actually, I think I have a slide for the reason why. Okay, so there's multiple reasons why you want to do that. The first one is like, I mean, there's a good chance that you don't need RL at all, right? If you find an existing model off the shelf, and we've had great performance with both Gemini 2.5 on some tasks, as well as O3 and O4 Mini. And if one of those existing models meets your requirements on the cost, latency, and performance point of view, I mean, you should just use it because it's going to be a lot easier than training something. I think training is getting easier over time. It's never going to be as easy as just using one off the shelf. So that's the first reason, is like maybe your project's done there. The second one is that like very often, it's almost universally, in fact, the case in my experience, when I first build like some complicated agentic system, there's just like some dumb bugs basically that get in there where it's like maybe our search tool isn't actually like, implemented properly and it's not returning the results that we expect. Or maybe the prompt is just really confusing and these models are just like doing something completely different and not what I expect. And I can just like fix that and like immediately get a giant boost. And so I think I have a chart here. So this is on the ART.E task. So the email validation task or the email research task. These are like the best performances I was able to get across the board on different models. But in order to get to this spot, like the sort of first version of this, the first version of the agentic loop, when I benchmarked all of these models, the performance, I think the highest I was getting was like 35% or something with one of the Gemini models. And it would basically just come down to like confusing things about the way I was prompting. The read email tool was like actually like not returning the whole email body. Like there were just some like dumb problems that were causing it to get bad performance. Running these prompted models and seeing, oh, it's only getting 30% of the time. And then importantly, the next step, once you see it's only getting it right 30% of the time, is you have to go look at the ones where it's getting it wrong and figure out what's going wrong here. You read the trace, kind of going back to way back here to this. So you definitely want some observability here, where you can see what the agent is actually doing. And like that makes it, like in my experience, you will almost always find when you're first starting one of these at least with a more complex project, oh, okay, yes, I'm missing something here. I can just make that change and get it fixed. So that's the first step. You want to do that and get that as good performance as you can. And then, so that's the second reason, that'll help with your train model down the line as well, because obviously like if your tool is not working properly, that's RL is not going to save you from that. And then the final reason, which is just a purely a psychological win, is it is super fun if you know what the best baselines you can get outside are as you're training the model. If you like see it surpass that baseline, you just like feel great about yourself, and it's a nice motivation boost. So always those are important too. Okay, and then like I mentioned before, really fundamentally the way you're doing this optimization and figuring out what you're working on is you got to be looking at the outputs you're getting. We actually use our own tool typically when we're doing this, our OpenPipe. In fact, I'll share another screen right now just to show what that interface looks like. But there's lots of ways to do it. ART.E actually built into the open source library. We have is this the right? Yeah. Okay. Okay, yeah. So this one's actually for a different project that I've been working on more recently. This is a model trained to be humorous, which I won't get into. Anyway, it's working like actually fairly well. But anyway, this is like kind of what our observability interface looks like, and it's really simple. Basically, it's just for the specific model for every single rollout we're doing, you see the input, and then you see. You see the output. Let's see if I find a good joke. Okay, yeah, these are all look bad. Okay, anyway, yeah, you see the, okay, this is, this, anyway, it's not important, but this model is made so you can type in a joke prefix and then it tries to like finish the joke for you with something funny. And so you can see here, we have the joke prefix and then we can see the output, we've got a bunch of thinking here and then it tries to come up with a continuation. Okay, so that's, but the important thing is not necessarily the tool you use. Like I was saying, we also have it built into into ART, the open source library, a way to, like, it's by default saves all of your traces on the training and validation sets just as YAML files, and you can like go in there and just read it, and that works fine as well. The important thing is you are actually looking at it. So once you've got that as good as you can, the next step is to actually like start training a model. So let's talk about how we did that, and we can ground this concretely in what we did on the ART.E side. So there's two major things you need to train your model. The first thing is some kind of data, okay? And I wrote down synthetic data here because oftentimes that's what you have to refer to. Worth mentioning, if you do have the ability to use sort of like real world data from an existing production system, then that's always like ideal. And by data, the nice thing about RL relative to say like SFT, which is another way of training models, is what you need, basically you need the inputs, right? You need what we call them scenarios, to the situation that the model should be trying to operate in. And you don't necessarily need the full output, like you don't need like a golden output if you have some way of measuring the output quality, which sometimes you do. Now, sometimes you don't have a way of measuring output quality in a general sense. And so one way to get around that is by having a golden output and comparing to that. We'll talk about that in a moment. But the first step is you do need synthetic data. So I'm going to talk about concretely how we did this in ART.E. Unfortunately, this is an area that it's a little bit hard to generalize on. It's very task dependent where you're going to get this kind of data from and what it looks like. So just an example, I'll talk about how we did in the ART.E case. This is sort of like a hybrid synthetic and real data thing. So if you think about it, the task ART.E is trying to do is, hey, I have a natural language query to know what the answer is from the inbox. So the pieces of information it needs to train on are like sets of questions, right? Like actual realistic looking questions. And then it needs to like know what the right answers are, or at least have some way of checking whether an answer gets us right. So the way we did this was sort of like I have written here, a hybrid system. We started with real emails because that was something we could get, and you want as much real as possible. So Enron, famous company, or I guess infamous company, infamously went bankrupt, went bankrupt, got sued out of existence, somewhere in between, in the early 2000s. And as part of the litigation where they went out of business, a bunch of their emails were made public as part of the discovery process. So there's this great online data set you can find of Enron emails. There's like 500,000 of them from different, mostly executives in the company, internal emails where they were talking about different stuff. So that's the real data, is we have these nice Enron emails. What we don't have from that dump is sort of the sets of questions and answers. And so that part we had to create synthetically. And so the way we did that in practice is we did a little bit of pre-processing and divided these emails from this big giant dump into sort of like which inbox they pertain to. And then for each inbox, we went through and iterated it, and we took it in chunks of 20 emails at a time. So we would get 20 emails. And then I used GPT 4.1 for this. I tried a couple other models as well, but I would basically take that chunk of 20 emails, and then I would tell GPT 4.1, hey, here's a bunch of emails from an inbox. Write some like very realistic questions that this user from their inbox might have about their emails that are answered in this. I gave it a couple of examples, like, what time is my flight on Friday, things like that, of the types of questions that are realistic. So I had it go through and write a bunch of questions. I then looked at the questions and I was like, okay, some of these are like good, but some of them are like kind of like sucky questions and feel just like forced and stilted. So I actually did a second pass on top of that, where I had it go back again. Well, I just edited the prompt and I had to do a second pass where after it created each chunk of questions, I was like, now, for each of these questions, give it a score between 0 and 1 on how realistic it is that you think like a user would actually ask this question. And for whatever reason, that actually worked like pretty well. So I set a threshold value of 0.9, where the way I set that value was just by like reading through a bunch of the questions and figuring out, okay, which of these actually feel realistic to me personally. So I set a threshold value of 0.9 and says, okay, if it scores itself as, yes, this question is like at least 90% realistic on, whatever arbitrary scale it's using internally, those look like pretty good questions. So I ended up with a subset of questions. You can see, so let me actually share I'm just going to put in the chat a list. I made that data set public so other folks can go through. But yeah, I'll actually go ahead and just share my screen so we can look at that real quick. So anyway, put up this data set. We've got about 5,000 questions generated totally. You see a bunch of questions, answers, and then, oh yeah, I asked it to also output exactly which message ID from that set of 20 messages it was given in the context, had the answer to the question. I then went through and had a second step where I validated and made sure that all of those message IDs actually existed and were in that context. And so anyway, the end result is I ended up with like a pretty strong, solid data set. Yeah, you can see this. We have this how realistic column where a lot of them are lower numbers, and we got some higher ones as well. Okay, so that's how we got our data set. Okay, so now we've got our data. And then by construction, in the way that we formulated this, we're also getting effectively like our what we call a reward function in reinforcement learning. Okay, so what do we mean by reward function? The important thing in reinforcement learning is that you have some way of knowing whether a given output that's generated by your agent, by your model, whatever, is good or bad, right? That's really, really key. That's critical. And the reason you need that is because that's kind of like central to the whole process. The process is you generate an output, you decide if it's good or bad, and then you are updating the model to produce more outputs that look like the good ones and less outputs that look like the bad ones. And of course, in order to do that, you have to know what's good and what's bad. So the way you determine, once you kind of like have your agent go all the way through its flow and produce an output, the way you determine whether an output is good or bad, that's just generically referred to as the reward function, right? The way of and the reward is how good or bad it is. So in different tasks, there's different ways of constructing this reward function. And unfortunately, that, in addition to getting the initial data, is the other, in my experience, really hard and tricky and very task-specific part. How do we determine whether it's good or bad? In this case, by the way we construct our data set, we sort of have like a built-in way of doing that reward function because as part of generating the synthetic questions, we also asked our model to generate what is the sort of like true answer based on these emails. And so what we can do is, when we're actually running our rollouts, now, unfortunately, these it's free text outputs. It's sort of natural language outputs. So it's not going to be like we can't use code to check if our output is the same or not. But because these questions tended to be like very concrete, very grounded in the inbox, what we could do is use a very simple, easily prompted LLM as judge. I just used Gemini Flash for this and said, hey, here's a question. Here's the sort of like ground truth answer that we have from our data set. Here's the answer our model gave. Do these answers match? Are they the same, yes or no? And again, this is a place where it was really important to look at the data. So I spent a lot of time kind of looking at, the LMS judge's answers here and tweaking the prompt slightly until it got to a place where it was like, okay, yeah, it's doing a good job of figuring out if these are semantically the same answer or not, and using that as a reward. And in practice, that seemed to work pretty well. Okay, looks like we've got a bunch of questions that I've just been ignoring. So let me really quickly go through our chat and see if there's good things to cover here. Okay. And then, of course, yeah, if you have general questions that aren't related to like a specific thing I'm talking about right now, or if I don't get to it right now, just because we're moving forward, feel free to please do drop it in the general Q&A, and we'll get to it at the end. Okay. All right. Yeah, some good comments here. Okay. Any good eval framework? Yeah, good question, Jack. Put that at the end. Yes, we will talk about that, but I want to make sure I get through the presentation. Okay, yes. So O3, so yes. So all those comparison models I was talking about, those are used with, so they all were put in the same Agentic RAG framework, given the same tools and basically the same objective. All right. So yeah, Seshadri asks about jointly training your RAG hyperparameters and the LLM. If you are doing sort of semantic search, yeah, you definitely could. The more degrees of freedom you have, like the easier it is to go off the rails often, which is one of the reasons why GRPO, in my opinion, became more popular than PPO, is because there's just fewer degrees of freedom. There's fewer hyperparameters because you don't have the same value model. But I mean, yes, you definitely could jointly optimize those. Let's see. Oh no, we're getting some drama between the Ragas maintainer and comments on Ragas. Okay, I don't have an opinion on Ragas. I haven't used it myself. I'm sure it's awesome. Okay, cool. So I'm going to go ahead and, okay, yeah, suggestions for generating synthetic data sets. Yeah, this is a good one I'll cover right now. So yes, generating synthetic data sets. I think what I will say is that my team here at OpenPipe makes fun of me a lot. I'm like generally like a pretty skeptical person. And like I just assume things won't work until they proved to. So I have like for a long time sort of assumed, hey, if you do like fully synthetic data sets, even if you try and bring in entropy and stuff, it's just like very unlikely to match your real distribution and to actually be useful for training. I feel like I've like proved wrong, at least partially on that, just through the experiments we're doing. So we have a bunch of different examples with other customers where we've tried where we just have zero data at all. It's just like, I mean, usually it's for privacy reasons, there's just nothing trainable. And we've just kind of like done sort of the best, but still like pretty dumb way we know how to do with synthetic data, where we just like, say like, hey, O3 come up with like 100 examples of, in this case, what realistic emails would be maybe, and with just the subject line, and then maybe like expand each of those into a full email, that kind of thing, which is not what we did here, but we've done things like that on other projects. And it's actually worked out like pretty great, even evaluating against realistic use cases. So yeah, so I think the key is, and this is like a whole separate conversation, but basically you definitely do need to explicitly try and get entropy. You need to try really hard. I mean, think as hard as you can basically about how do you prompt this to get things that are as close as possible to the distribution of your real data that will be used in production that you can't train on for whatever reason. And then obviously if you can use real data, that's always going to be better. Okay, cool. I am going to go ahead and move forward. All right. Yes. Very briefly, we're going to cover the training loop with GRPO. So GRPO is a really, I think it's kind of elegant, but it's fundamentally very easy to understand. The way it works is for every scenario, for every input, you generate n different outputs. In this case with ART.E, we generated 4 different outputs for each one. We scored every output if it was correct or incorrect. And okay, this is the part that's a little tricky. I'm going to hand wave that. But you then basically like calculate your loss function. So the way you tell the model what's good or bad is based on whether an answer was right or wrong. And basically you're training it, you're optimizing it to produce answers that are more like the right ones and less like the wrong ones. And that's it. That's really all you're doing. You do that in a loop a bunch of times with, in our case, all of these different question answer pairs. There's different ways you can set up those scenarios. But basically you just do it over and over and over again. And if you set everything up right, then eventually your model just figures out what it's doing and gets better at it. And that's exactly what we saw here. So this is something you can see in our blog post as well. The fraction of answers and questions answered correctly, where you can see that over time, we started because again, this ART.E is a very small, pretty weak model based on where it starts from, right? It's just a 14 billion parameter Quen model, and all of these other closed source models we're comparing to are likely significantly larger. So it started out doing significantly worse, where only about 40% of the time it was able to successfully navigate and give a correct answer. And then as training goes on, as it's sort of reinforced with when it does the good thing, it gets scored up. When it does the bad thing, it gets scored down. You just see that over time it improves. That's what you're looking for. You don't always get it. So one thing worth mentioning is this was, we ended up training about 13 different models with different hyperparameters to like try out different things and different, not just hyperparameters from like a pure training point of view, but also like what is the reward function we're using? Like, are we, we tried things like, hey, if the reward is too similar across different generations, maybe we'd like throw those ones out. That was like one research result we were experimenting. So there were different things we tried. And we find that very often there is a lot of experimentation necessary, but if you get it right, this is the sort of result you're hoping to see. One really nice thing about reinforcement learning is that it can do a really good job at optimizing for multiple different objectives at the same time. So this one I'm looking at right here, this is a graph of our primary objective, which is just, did it get the right answer, right? And so that's the main thing we care about. But another thing we care about is, going back to the beginning of the presentation, hey, latency. Can we do it in fewer back and forth turns? So as part of our reward function, deciding if an output was good or bad, we gave a small, very slight bonus if the based on the number of turns, the number of like back and forths that the model had to do with basically the tools it was given. And so if it used fewer turns, we would give it a little bit higher, like a little bit of a bonus, assuming it still got the right answer. And so you can see the model was able to learn from that signal quite well. Early on, it was it had to do a lot of exploration here early on. And we can go back to this graph. You can see initially, okay, I've got to go back and forth a bunch of times to kind of like figure out how to get the right answer. And that's what we want it to be doing. It's more important to get the right answer than to minimize the number of turns. But then once it kind of figured out how to use the tools properly and how to like use them in an optimal way and what sort of keywords were most likely to get good results, you can see over time it's dropping the number of turns down to just like about 3.5, which actually 3.5 is pretty close to optimal play here. Optimal play would be 3 probably, because it has to use 1 turn to run an initial search. It technically doesn't have to, but probably should use another turn to like read the relevant email. And then there's always a 3rd turn to return a final answer. So it's on average just using about half an extra turn, which is a better performance from a latency point of view, and resource usage cost point of view as well. So really cool. You can optimize for multiple objectives. You can throw more things into the mix. The blog post goes into a lot more detail on other secondary objectives we added, but most of them were either just to like make conversions faster by giving a little bit of partial credit for being on the right path, and then this one to get fewer turns. Oh yeah, and well, this is another one I'll call out, I guess, since I think it is important. So in addition to, so one thing, again, on this sort of like you can optimize for multiple things, getting the right answer is obviously what we want. If you can't get the right answer, it's definitely much better to just say, hey, I don't know what the right answer is, than to just make something up or answer wrong. And so we gave a heavy penalty for answering a wrong answer that was actually much worse from a reward point of view than just saying, I don't know. And so you can see the model was able to successfully learn not just to get the right answer, but in the cases where it didn't know, it was less likely to basically hallucinate and give a wrong answer than any of the comparison models that we were testing as well. Okay, so this is just an example of kind of the kind of thing that can go wrong. So you can see this is a different graph. This is from our weights and biases dashboard where, and this is for a different model. I think this was our 2nd run, and then the one we were looking at before was our 8th run. So you can see this is a very different graph on the number of turns, where it starts down around 4 or something, and then gets up and it sort of just like plateaus at 10. So what was happening here is I was just, as an example of things that can go wrong, I was trying to incentivize it. If it didn't get the right answer, I would actually give it a little bit of extra credit for doing more turns, under the theory that like, hey, it needs to learn to explore more until it gets the right answer. Basically what it learned was like, oh, I get a little bit of extra credit for exploring. And so it kind of just like ignored the right answer, because I think I had the reward. I also had like the wrong ratio of values on the reward. So it was just like maximizing. And then I put a hard stop on 10 turns. So it was just like basically maximizing and just like always trying to get 10 turns. And it would even just repeat itself, as you can maybe see that in the screenshot, where it's just literally doing the exact same thing over and over again until it got to 10 turns, just because it, decided that that's how it would get rewarded. So anyway, yes, things to watch out for. Again, super important to like sit and look at your traces, which is the, on the practical tips we have, that is the first thing, which, hopefully you'll take that away from this, is for debugging this stuff, just like looking at your model's actual behavior, and then thinking deeply about what's going wrong is, I think, the critical prerequisite to debugging any of this stuff. I mean, if you're looking at just your loss curves and things like that, your reward curves, you're just not going to know if it's actually doing what you want it to. You have to think really hard about the reward function. That's just super important. And again, it's very dependent on your thing. Sometimes, like I said, if you do have a golden data set, you can use that similar to that, but there's lots of other cases. We've done things like with games, with self-play, things like that. There's different ways to construct that reward function. And then, okay, metrics also. I'm feeling time pressure, I apologize. If people want to stay a little later during the Q&A, we'll definitely let the Q&A go over for folks who are able to stay. Anyway, lots of metrics. So again, more details here in the blog post. I tracked, I think, like 8 or 10 different metrics as part of, in addition to just sort of like the top level reward. And that just gives you a really good sense of what's going well, what's going poorly. Obviously, the number of turns when I talked about the sort of hallucinating a wrong answer, I talked about, and there's a bunch of other ones that we just tracked and reported to weights and biases as we were going through. So that's the general idea. Cool. All right, so that's I think the main things I wanted to get through. Okay, yes, and then RL for your domain. Yeah, very briefly, the main things you need diverse scenarios, not just diverse, but like actually as close to in-domain as possible for how your model will be used in production. And you need to think hard about the reward function. I think we've basically covered those already, so we don't have to go too deeply there. Okay, yes. If you want to learn more, and I think we can send out a link to this presentation after. Okay, so we'll send out a summary email, but yes, you'll be able to get, there's a blog post that goes into a lot more details on everything we talked about here. And the ART trainer itself, if you're interested in this, everything, like all of this is open source. And by the way, the whole ART.E project is also open source, linked to from that blog post as part of that ART repository. And then yes, I talk about this stuff on X a lot. If you're an enterprise, you're interested in deploying one of these agents, maybe you have deployed one of these agents and are interested in improving its performance. That's something that's basically our bread and butter here at OpenPipe. Is we do white glove engagements. We help you get this stuff working in production and work with your team both to deliver full solutions, and also if you want to build these capabilities internally, we can definitely help with just consulting and helping your teams get up to speed as well on both of those ways. So please do reach out if that's something interesting to you. Yeah, just hello@openpipe.ai. We'll get you connected to our team directly, and I'm very excited to chat about any of this. Okay, so that's all of the stuff I wanted to cover in the presentation. We've got about 10 minutes left on the hour. Like I said, if there's still questions left after that, I'm happy staying later, but I'll try and get through as many as I can in the next few minutes. For those who might have to jump, we'll also have this recorded if people want afterwards. Okay, first question from Adrian. Adrian asks, as a result of training, was the model selecting better keywords? I mean, fundamentally, yes. There was a couple of things it was learning, and one of the other metrics I tracked, which, okay, let me see. I'm going to share my screen. One of the metrics, so basically, yeah, the way it was getting better was two things. It was getting better keywords, and then it also was just getting better at understanding kind of like the function calls in the first place, right? Okay, so here's all the different metrics I tracked for, and this is just that final run that worked well. So, okay, source is correct. Basically, was it able to, oh yeah, one of the things I asked it to do was not just give the answer, but actually cite its sources. So that's part of the output as well, is, hey, these are the, this is the message or messages that the answer is contained in. And so you can see it's basically almost perfect on that. It gets up to about 90, at sort of maximum 97, 98% at finding the right emails. And then, but yeah, one of the things that that I was tracking was, yes, whether it was using the right tool call, right? So you can see, so it basically was always able to do that. So, oh, we do have, okay, so yeah, this is a good one. So bad tool call argument. So if it tried to call, say, the search email tool and then passed in the wrong format or something, I would mark that. So you can see early on, about 30% of the time, it was just had no idea it was using the wrong argument format or something. That quickly dropped and never dropped all the way to zero, at least not consistently. But yeah, down certainly below 5% of the time, it was making mistakes with the tool call format. Okay. Murata says, how easy it's to game the reward function? Yes, great question. So this is called reward hacking. That's what in the RL literature they do, where it's like, yes, it's getting the higher and higher reward, but the way it's doing that is by basically finding some way to solve the problem that's not really solving the problem. We had a fun example of this. Someone else on our team was building a game with the NYT, what do they call it? Connections, yes, puzzle, which is basically you get 16 words, and you have to put them in 4 groups of 4, but you don't know like what connects the words. So anyway, he got super excited because he was looking at this reward chart, and it was like, oh, this model is just like nailing it. Like all of a sudden, after 30 iterations or something, it was like 80+% of the time it was like actually getting the answers right. Well, it turns out what the model was doing was it had realized that it could just, you're supposed to output like a list of like four lists of 4 words each that are in the correct groups. The model had realized that we had basically the way we had written the reward function was flawed. And instead of checking that the groups were exactly the same, it just checked if the correct words were in each group. And so it was just outputting 16 words in all 4 of the groups. So again, looking at your outputs is a good way to deal with that. So in my experience, that said, usually what I find when I'm doing this is that early on in the process, there's like there can be some hacks like that. But then if you like either, I mean, in that case, just update the code, or sometimes it's as simple as just like, sometimes it's like, oh, yeah, that's not what I was looking for, but there's not a good code way. And you just add like an extra LMS judge that says like, hey, this particular behavior is bad. Another example, I was working on a model that actually worked really well. It we're very bottlenecked on writing things up. I was working on a model like a month or two ago to generate titles for Hacker News. So you have a Hacker News, like just a post body, and then it tries to generate an engaging title. And then I trained a reward model based on real Hacker News stories to try and guess, hey, how upvoted this would be. And basically what the model learned, at first it was doing a pretty good job and it was improving and like getting better and better titles for the story. And then at some point, like looking at the traces, it was actually really funny. There was like this explicit point where it found there was a title that just like maximized the reward. And it was something like, I don't remember the exact title, but it was like very like engaging bait. And it was something like, Google lays off 80% of workforce, 70,000 engineers without jobs, and then in parentheses 2023. That was like the title, and it was just applying literally that exact same title to every single story, independent of the story content, because it had realized that like the reward model is like, oh my goodness, this is going to get like the most upvotes ever, which is true. If there were a story with that title, it would probably get a ton of upvotes on Hacker News. So anyway, the solution there was I just had to add an extra like auxiliary LMS judge, which was, hey, take this story body, this title. Does the title apply to the story? Is there anything in the title that's unsubstantiated? And after I added that, it actually like pretty much didn't have any problems anymore, and it wasn't reward hacking. So that anyway, that's been my experience where yeah, sometimes you do have something like that, and you just need to like add a few explicit fixes, and then you're good. Okay, text-to-speech context, user won't be choosing. Okay, Alex, sorry, we'll have to take this offline. I think it sounds like a more complex question, very specific to your text-to-speech. Okay, context length limit, Min asks, is an issue. Is context length limit an issue with multi-turn agents? I mean, yeah, it can be. In ART, specifically, we're building on top of TRL's GRPO trainer and also the unsloth optimizations on top of that. We found that on an H100, we're able to get up to 32K context training pretty easily. We should be able to get probably up to like one day with like an H200. Obviously, we're working on multi-GPU support as well. But yeah, we find for the things we've been working on, at least, it seems to be it hasn't been a major limitation yet. Okay, Tim asks, if I train a model with OpenPipe, can I get the weights? Yes, absolutely. Any model trained through OpenPipe, you can export the weights. And with ART, it's actually, I mean, the ART library is fully open source. So we don't even train the models for you in that case, or at least you have the option to do it fully yourself using that. Okay, Jithan asks, generalization. Bigger models should be more generalizable, so should work better in the wild in theory. Yes, that is true. I think it really does come down to how general the task you're trying to perform is, right? And I think, so let's see. One thing I will say is that like for ART.E, we did ablate against lots of different model sizes up to 32 billion parameters. We didn't see with the 32B any better performance than 14B on our validation set. Now, you could also argue that our validation set is more in domain potentially than the actual questions a real person would ask, because ultimately our validation set was also generated by the same synthetic data process as our training set, just with a different set of inboxes. So I think that would be the way I would answer that question, is I would probably train and deploy both of those models in production and see if one of them was working better in prod. One thing I would say on the other side of that is it is true larger models generally work better, but you also, I mean, you have to look at this holistically, because you can run a lot more experiments and ablations on smaller models than larger ones just because they're a lot faster to train. And so that's, that is a trade-off on the other side, where it may make sense to go with a smaller model that seems to be working well just because you can test a lot more hypotheses more quickly. Okay, it says, Anonymous asks, how do you know when to optimize the prompts the agent uses instead of just optimizing the weights? So one nice thing about RL, I think I touched on that early on, but one, you do want to optimize the prompts first. That said, the model that's trained using RL is generally much less sensitive to the prompts than, post RL, less sensitive to the prompts than like a prompted model, just because it's like ultimately it starts learning from the reward function more from the instructions in the prompt. And so yeah, once you get to the point you're doing RL, it's likely, I don't think you'll get much more juice from editing the prompt at that point. Okay, Bharat says, it feels like OpenAI deep research is also agentic RAG. Yeah, yes, I think this is going to be, I think it already is a common pattern and it's just becoming more so. Okay, mixing RAG versus agentic RAG. Yeah, theoretically you could have both in the same system. I don't think it'd be hard. Like what you could have is just like your agent generate sort of the snippet that is then compared using semantic search to your corpus. I think that could work fine. I think I would advocate if you work with my customer to like not add that level of complexity until you prove that you needed it, because now you have kind of two complex moving parts instead of one. Okay, let's see. All right, are we working on making OpenPipe more responsive? Yes, Alex. Yes, we are. Okay, so constant ask do backprop over the rollout as is with tool calls and tool call outputs. Yes, okay, so we do mask out. This is sort of a technical question as you're doing the training. Are you training on sort of like all the tokens, both the system prompt user messages, tool responses, or are you just training on the assistant messages? This is a great question. And yeah, it's really important that you train on just the assistant messages, because ultimately that's the part that the agent has control over and the part that the agent produces. So you do want to mask out and only tend or only like take into account the loss on the tokens that the agent produced. And as sort of like a practitioner using the stuff, you probably don't have to worry about this. You just want to make sure your library does that properly, which we do in ART. Okay, cool. And I know we're over. If people have to leave, that's totally fine. We just have a few questions left, which I'm gonna definitely try and get through. All right, do you use any tools to experiment on different prompts and tool parameters? Okay, Tyson. Yeah, I think within ART itself, in fact, I'm going to go ahead, didn't prepare this ahead of time, but let me real quick. Yeah, I've used a bunch of tools, and frankly, I've always come back to like writing my own on a task by task basis. Let me share how we're doing it for this particular project in case that's helpful. One thing I will say is that one nice thing about RL is it's sort of like if you get RL working, you've sort of, at least it basically requires you to solve to some extent the eval problem, because you need to be able to evaluate if your model is doing well or not to generate the reward. And so usually it makes sense to use that same reward function, or at least often it makes sense to use that same reward function or some piece of that reward function as your evaluation. So this is the benchmarking code we have here. And again, it's quite simple because we already, within our rollout itself, we have code to determine if the output is good or bad, right? So the benchmarking then becomes as simple as, we're taking a model, which can be either prompted or a trained model. That abstraction, ART.model has both. And then we're going to load our test set. We're going to grab 100 of those. And then we're going to use this special gather trajectories, which is basically a way of just running our rollout function against all of these scenarios. We can gather trajectories, and we're running rollout against all of them. And then, and then we make sure we only have valid ones, because it will, if one of them throws an exception, we don't want to count that. And then we get our metrics, which is something that happens within our rollout function. We average them, and then we return it, right? Benchmark, and then we have this wrapper where this is literally how I generate all the benchmarks you see in the post. I've got all of these different models. We have sort of the pretty display name, and then kind of I'm using light LLM under the hood for this. So the light LLM name for each of them. I am then going to, I need to update this with the new repository structure. Yeah, so for each of those models, I'm going to go ahead and create sort of an ART model that is based on it. I'm going to run that benchmark model we were just looking at on each of them. I'm going to stick the results in a data frame, and then I just basically like print the data frame as markdown, and that's how I get the results. Create log charts. I'll also show you, and then we also have some nice helpers that we just built inside ART that generate graphs for you if you have a set of outputs, and also let you like look at your things. So anyway, this is more than the reason we need to get, but basically all the graphs from the blog and everything are just directly generated from the traces and metrics that we are logging in ART, and we have nice helpers that let you make your own cool graphs too. Okay. All right. Per sample rubrics as a reward function, do you need to create a greater model? Yeah. So this is really specific to your application. We've done a lot of both. So, I mentioned like the HN title one, also that joke model I was mentioning. Those ones we both trained a grader model to start with. A reward model is what we call it. And sometimes if you can do that, that's generally what I recommend. So in the HN title one, it was great because it was like, hey, I'm just training a model based on the number of upvotes this story got, given the body and title. For the jokes one, I trained a reward model based on, I grabbed like 100,000 jokes from this joke, like r/joke subreddit, and then trained model to predict, given a joke, title and body, how many upvotes it would get. Once you have that reward model, sometimes I find that's sometimes easier to work with, but sometimes you can't do that, right? And so like with the ART.E project we're talking about, we don't have a way of training a reward model. And so we instead use that sort of golden answer that we have in our data set and compare to that. So again, very, very task specific. Okay, Murat asks, how, why Quen? I guess you're asking why we use the Quen models. Yeah, we've tried a bunch of them. I mean, we've tried Gemma's models, we've tried the Llama models. We just find that Quen in general seems really good at most of the tasks we're using. The Gemma models are good at some things too. Yeah, the Llama models I think are just probably a little bit outdated now. We haven't actually, I didn't get a chance for this project to use the new Quen 3 models. These were all with Quen 2.5. I would expect Quen 3 will do even better. I just haven't had a chance to get to it yet. Okay, Adrian asked, did the performance of the model generalize to other mailboxes? So yeah, that's open question. So within other mailboxes, like within the Enron dataset, yes, definitely. So I kept a set of mailboxes that weren't trained on at all. So it never saw any of the emails in those mailboxes and used those for the validation set. I did not use like other non-Enron emails. I suspect, again, based on kind of experiences we've had on other projects, that it would generalize pretty well. That's been my experience, but yeah, didn't get a chance to try it on this one. Okay, Jack asks, I have an Elasticsearch Retriever as part of a RAG pipeline. I'm using both lexical and semantic search, measure whether my search results are really good. My question is, how do I start with evaluating that? I need a programmatic way to quickly get started and measure. Okay, so what I would do in that case is basically try and put together a golden data set. So I would try and figure out what are some realistic questions someone might ask, and then grab the top whatever number you need to like get what you think is relevant to that, and then figure out what the and then probably manually, or you could also, I think I would probably at least for first pass get LLMs to go through this, and I'd maybe use like get Gemini 2.5 Pro and be like, hey, this is the question, which of these is most relevant, and then double check its work, and then basically build a data set from that. So for this question, these are the top end documents that should have. And then as you are optimizing your system, you can run that as a evaluation, right? Where it's like, okay, I've got this query, and then goes through whatever process, Agentic RAG, semantic RAG, a mix of both of them, whatever you're doing. What are the final documents it came with? Did those documents are they the ones that I expected or not? And again, I did do a variant of this, which you might remember I showed a moment ago, where one of the metrics I was tracking was not just did it get the right answer, but did it like cite the correct the correct email as part of its output. Okay, if OpenAI deep researches an agentic model along these lines, what do we think the reward function is? Yeah, it's a good question. I mean, they haven't been super public with it. They have said that they're using LLM as judge for a lot of things, which is another one of those areas where I was initially kind of skeptical and have grown more optimistic over time. But yeah, I suspect one thing they might be doing is having it go through multiple different research processes and then coming out with the outputs from all of them, and then basically giving it to another a third instance basically of OpenAI's O3 and say like, hey, given this question, which of these outputs is stronger, is like better reasoned and better cited. So yeah, that might be one way they're doing it. They definitely have said that LLM as judge is part of their thing. Now, OpenAI also uses a lot of human expert data. It wouldn't surprise me if they, augmented that or used a great deal of human judgment and paying experts in the field lots of money to look at the outputs and decide which one is better. Okay, and this is the final question. If anyone has more questions after this, feel free to drop them in.
Maybe Discord?
Oh, yes. Actually, joining the Discord is a great idea, like Daniel said. So Min asks, do we have a roadmap for the ART project? Yes, I don't know if Brad is still on this and if he's in a chance to talk. He's leading the ART project, but yeah, there's three broad areas that are pretty high priorities for us. Multimodal is a big one. Lots of people asking for it. It's not that hard to add. We just need to do it. Full fine tuning is another one. Right now, we just do LoRa's. There's a lot of advantages to LoRa's. Honestly, for most of our projects, we'll probably continue using LoRa's just because it's so much more resource efficient and just lets you train larger models more quickly. But there is a hard limit to how far you can push behavior with a LoRa. Some people want full parameter. Multi-node training, and in general, just like training acceleration, I would say. So using more GPUs to go faster. There's a lot of interesting things around async RL, which is more in the weeds than we're getting to on this conversation. But right now, it's kind of like you're taking turns between doing the training and doing the generations. If you can do both of those at the same time, you can substantially speed up training at the risk of some, you lose reproducibility, although you kind of already don't have it with this stuff because you're sampling at a higher temperature. So, and in practice, that seems to work well. So anyway, basically things about making it go a lot faster are the highest priorities for us. Cool, awesome. Thank you, everyone. Really appreciate the questions. Really appreciate everyone staying after. Yeah, we'll send out after this more details. We'll send out those links. And like I said, if anyone wants to work more closely with us, please do email us hello@openpipe.ai. If you want to be working on your own using ART, it's all open source. We want more people in the community. Join our Discord. Please try building models with it, and we'll do our best to support you and make you successful because yeah, it's fun stuff to work on. Thanks, everyone. Bye.